The purpose of my talk today is to consolidate what I talked about in the first two lectures. I will not introduce new material, but I will try to give the meaning of the things that I did. Now, mathematicians usually are not concerned with the meaning of what they do. They are students of professors. The professors supposedly know the meaning, but they got their meaning from a teacher too, and it goes back and back and back, and then we forget what it was all about. This is a problem because mathematics is expensive, and somebody has to pay for it, and those that pay for it will decide that they have better uses of their money. So that's one of the reasons why one try to understand the meaning of mathematics so that we will stay in business. In my first two lectures, that was on Monday, I spoke about a spectral theory of differential operators. Now, I'm sure that all students of analysis and even others know what the spectral theory of a differential operator is. Often they are second-order differential equations, like the Schrödinger equation. But better, they are a pair of first-order differential equations, like the Dirac equation. And people discovered that there was a spectral theory of these differential operators. They discovered that very early in the 20th century, maybe before in the 19th. And what I spoke about is a spectral theory of differential operators that's based upon the theory of orthogonal polynomials. Now, when I began my career, that was more than 50 years ago, people did not understand what a spectral theory was. They had a very crude theory. And at the beginning of my career, I wrote what I think is a good spectral theory. A lot of people don't know this spectral theory. It's a shame that only after these 50 years that there is some recognition of it. There was some recognition, of course, in 1984. During my last visit to St. Petersburg, there was a seminar in functional analysis by Nikolsky, and it's also with Professor Havin. And those students of Professor Havin, we have one here, know what the spectral theory is. And there's even going to be a symposium in Poland on that subject. Now, this is the first time in my career, in my lifetime, that my work has been recognized. It has been published in books, but I'm sure that nobody has ever read it. So you have, if you want to learn this theory, you have access to a completely new theory, as far as anybody knows. Now, this theory is a reformulation of the theory of orthogonal polynomials. And in that theory, in the 19th century, people used the hypergeometric series. If you've taken a course in analysis, you have certainly solved differential equations using power series solutions, and the examples that were given to you were always very nice examples. They were hypergeometric series. And if you don't have a hypergeometric series, it is very difficult to get a solution. So you were shown the few examples in which there are solutions. Now, these special cases are important. The reason why the solution is computable is because there's some kind of symmetry present. And if you want to be successful in the applications of mathematics, you have to understand the principle of symmetry. If you're dealing with an object that has no symmetry, you're not going to succeed. But if you see that it's cubic or round, that greatly simplifies the treatment of it. Now, the recognition of that symmetry, unfortunately, has been lost in the 20th century. And in my work on the spectral theory, I go back to examine that those conditions, and in my treatment of spectral theory, I treat examples of systems that have a good spectral theory, that have that symmetry, and in fact, they deal with an axiomatization of the hypergeometric series. Now, when I was a child, that was before the First World War, the Second World War, I mean, I was, before 1941, I was brought up in France, and I learned to think as a Frenchman at that time, and French people like to axiomatize everything. They think, like Descartes, that you can describe the properties of things to get their essence, and that will help you understand what those things are. So in every mathematics that I do, I axiomatize it. This is a very slow, painful procedure, but it is very helpful to those that need to learn things. And so I recommend that you look at my treatment. Let me mention the applications of the spectral theory. There are two applications. The main one, the one that I care about, is in quantum mechanics. I'm interested in how electrons move around atoms and molecules. In fact, I came into mathematics because of chemistry. And in the field of chemistry, there was not any adequate mathematical theory, so I decided that I would do mathematics instead. And it was a good choice. But there's another application of the spectral theory, and it occurs to number theory. Now, number theory is a very old part of mathematics. In 1730, Euler discovered, he was at that time in Basel, he discovered the gamma function. I think he was in Petersburg, St. Petersburg, when he discovered the zeta function, and probably also when he discovered the hypergeometric series. Certainly, he was being paid by Catherine the Great, but he kept that scholarship also when he was not in St. Petersburg, when he was in Potsdam. These two theories lie together in the 19th century. And if you read books for that time, you see that the authors expect a relationship between what they called applied mathematics, it wasn't yet quantum mechanics, applied mathematics, and number theory. Now, in the course of the 20th century, there has been a great expansion of number theory with very little progress in analysis. And the result is that many people know number theory and they don't understand applied mathematics. They think that that application is somehow a little bit lower, a little bit higher to be doing number theory. This is disastrous because I believe these two subjects are related to each other. And in fact, I think that the significance of number theory is that it treats symmetries, discrete symmetries, like the symmetries of a cube, as compared with the symmetry of a sphere. A cube can be rotated into itself, I think, 24 times. It's a non-commutative group. And that generates another kind of structure than you have with a sphere where you can rotate arbitrarily. Now, when you deal with a molecule, I believe that you have to use both kinds of symmetry to understand the structure, both of an atom and a molecule, as a place where electrons are moving. Now, in my other lectures on Wednesday, I talked about Fourier analysis. This is an entirely different subject, but Fourier analysis, which were discovered in the beginning of the 19th century, consolidates the mathematics of the 18th century, because it turns out that the hypergeometric series is important for Fourier analysis, and that Fourier analysis is very simple. And so it helps greatly to have Fourier analysis when you want to deal with the hypergeometric function theory. Let me remind you what Fourier analysis is about. It's about commutative groups. These are commutative groups, usually with a topology. So the word that you use is a locally compact abelian group. These groups have a canonical measure, essentially unique within a constant factor. There's a space of square integrable functions with respect to that measure, and the Fourier transformation is an isometric transformation of the space of square integrable functions into itself. This transformation is remarkably important, and the reason for that is that it's concerned solely with the additive structure of a group. An additive structure is very simple. I mean, if you work with additive structure, you're bound to understand it after a period of time. But the reason why additive structure is important is because there is also a multiplicative structure. The multiplicative structure, that's given by the homomorphisms of the additive group into itself, or the isomorphisms of the additive group into itself, and they often form a group, and there are two kinds of elements of the group. There may be a subgroup that's compact, and there may be a subgroup that is locally compact without being compact. Now I'm going to take the example of the plane. The plane is an example of a locally compact abelian group. And I won't need to make a picture here, but you put coordinates. You have a y-coordinate, an x-coordinate, and there's an origin in the group, a neutral element for addition. Now, what does it mean that there is an origin? It means that whenever you deal with an abelian group, there's an important point in the group. It means that the group is a solar system, and this is the sun that is sitting inside at the center of that. And around this object, around this sun, there are planets that are moving around, and we want to know how they're going to move. We're actually not interested in dynamics. We simply want to see the symmetric structure, the paths that's caused by these objects. And when you're working with the plane, in the complex plane, you have your group of rotations. These rotations form a compact group. That means that the group, the invariant subspaces of the group, are finite dimensional. In fact, they're one-dimensional because the group, the characters of the group, I'm being too complicated. Because it's an additive group, there's a very simple structure for the invariant subspaces. Now, the group is the group of rotations about the origin, and the subgroups are given by, maybe we can go back a bit. Do I show that? I just didn't, we just have these pages here. But the rotations form a compact group, and so the characters of the group are determined by the integers.
This is the first one.
Well, maybe.
You can go back.
It could be about page 16, something like that. Okay, so this is the Fourier transformation. I try to make these good notes so that if you want to read it, you should be able to get the information. Okay, this is the Fourier transformation. I use a notation that would apply for a more general group. And I don't see, you did a little bit more. Okay, we've gone by, wait a second. That's enough. In the space of square integrable functions, you have the space is the orthogonal sum of subspaces defined by the integers n, and the functions that belong to the subspace, they have the property that when you multiply the argument by omega, omega is a number of absolute value 1. In other words, it belongs to the circle, or in other words, its conjugate is equal to its inverse. And when you act on the argument, the xi, it multiplies the value of the function by omega to the n. That's a character of the multiplicative group defined by n. So the group, the space of square integrable functions, is the orthogonal sum of subspaces defined by the integers n. The Fourier transformation maps every subspace into itself. You also have another transformation where it's written down here if you go a little bit farther. So the isometric transformation. You're going too far. You're going fc. Well, if you conjugate the argument of the function, you have an isometric transformation that takes the space of square integrable functions into itself, and that also commutes with the Fourier transformation. But this conjugation maps the invariant subspace for n into the invariant subspace for minus n. So the invariant subspace is defined by n and minus n, when n is non-zero, are different, and there's no reason to work with both of them because they're isomorphic to each other. So I assume that n is positive, or maybe 0. And in the case where it's positive or 0, I want to hold the n fixed, and I call it nu. Nu means a non-negative integer that stays fixed in the discussion so that I can use n for other purposes. Now, there is, keep going. So now we go, okay, now the Fourier transformation is defined by an exponential kernel. I have written this kernel using complex numbers for xi and eta, and I use the conjugation to make that. So you may not recognize that at the top, that is the Fourier kernel. In that notation, maybe you want to put x and y in there, and it would be more familiar, but I didn't do that. And when you take the action of the circle group, that decomposes into components. Components for every non-negative integer omega, you have this decomposition. Now, this decomposition is found in books on advanced calculus. I like Whittaker and Watson book, 1905, Modern Analysis, as it was in 1905, and it's still pretty modern. Now, when you make this decomposition, some new functions come in. They're called Bessel functions. Now, I don't like the notation for Bessel functions that was found in the 19th century. I usually respect notation, but I'm sorry to say I'm not able to live with the classical notation there. It just makes everything very complicated. So I use a variant of the Bessel function. And the variant of the Bessel function has n factorial, nu plus n factorial, those essential denominators. And, but there's no factor of z to the nu in front. And I make the argument z rather than 1/2 z. So take that 1/2 out that's in the books, take out the power of z to the nth power, and it leaves you with a function which I find preferable. So that means when you want to read what I have here, you have to make a complete change of notation. I apologize for that. So now, that Bessel function then describes the Fourier kernel as it acts on functions that have a symmetry defined by nu. And the Fourier, when you write the Fourier transformation, you get a new transformation. Keep on going, keep on going. I just want to observe that these Bessel functions satisfy differential equations, that they are used whenever, oh, I made an error in my manuscript. I wrote a to the minus 1. It should be nu to the minus 1 on the right there. So there's a small error. I tried to keep the errors out, but I didn't get them. So now go on. Now, there is a Huncle transformation. The Huncle transformation in this notation takes a function of positive t called f into a function of positive t called g. These functions are measurable functions, and they're required to be square integrable. So keep on going a little bit farther. It's an isometry. Okay, I want to go back. We want to go back to that. We want to stop at that last formula. What I didn't write here, but it's written in words. At the top of the page, you see that the integral square of the function f of t is square integrable when you put a factor of t to the nu in there. In my notation, the classical notation tries to keep Lebesgue measure as the measure, and that really is a terrible mistake. So I make a change of notation, and now you take square integrable functions with a weight, t to the nth, and the expression for the Fourier transformation becomes what's called a Huncle transformation, and that transformation is isometric. It takes the space of functions f, which are square integrable, onto the space of functions g, which are square integrable in the same sense. And when I write the Huncle transformation, it's not quite the same as the Fourier transformation. The Fourier transformation, you would have I to the nth power multiplying the integral, and that constant of absolute value 1, I just omitted that because if you do that, the Huncle transformation is its own inverse. That means that a function that's square integrable is the orthogonal sum of a function which is its own Huncle transform. That's called a self-reciprocal function, and a function which is minus its own Huncle transform. That's called a skew reciprocal function. Now, the Fourier analysis is done with the Radon transformation. Fourier analysis, according to Fourier, never uses the Fourier integral. He uses what's called a Laplace transformation. That Laplace transformation he introduces because he says he wants to study the flow of heat on the complex plane. He worked with the line, actually, but I'm in the plane. And in order to study the flow of heat, you have to propagate heat by a certain differential equation. I think everybody's seen this in the books, and you were told that this was applied mathematics. Well, it's true, but the reason why it's called applied mathematics is that Fourier was a friend of Napoleon, and it was very important to have Napoleon give money for mathematics. So he pretended that this was applied mathematics and that was able to publish and get the recognition. But the problem with that conception is that as applied mathematics, people thought that it's unimportant, whereas this is actually theoretical mathematics. And so in the present day, there are essentially very few people that understand that the flow of heat is a theoretical tool. You have a flow of heat on every locally compact abelian group. It's a universal property of Fourier analysis. It's not just a property of the line. And all computations of Fourier integrals by people that use them, and these are applied mathematicians, they always use the Laplace transformation to compute the integrals. In other words, they break down the function into a function that has a symmetry, and when it has a symmetry, you can use the Huncle transformation instead of the Fourier integral. And in order to deal with the Huncle transformation, you introduce the Laplace transformation. Now, unfortunately, many people don't realize why there is a Laplace transformation. It's because the flow of heat is the Laplace transformation is the spectral theory of the flow of heat. Now, the flow of heat is described by a differential operator, and locally compact abelian groups do not have a differentiable structure. So it would seem that there isn't any flow of heat on a locally compact abelian group. But this is not true, because the inverse of a differential operator is an integral operator. And integral operators are meaningful on arbitrary locally compact abelian groups. And this is the way on every locally compact abelian groups that you should be computing Fourier transforms or dealing with a theory. Now, I have used a special change of variables, and in my notation, the original operator for the flow of heat is not visible. When I make a change of variable, what I get is the analogous operator is ordinary differentiation, and the inverse operator is an indefinite integral. But the conception here, the integral transformation, is what's called a Radon transformation. And these Radon transformations are used very much by applied mathematicians, but they're not known to theoretical mathematicians. In this case here, the Radon transformation is a very elementary transformation. Now, this transformation has a spectral theory. Spectral theories exist for very special transformations. The Hilbert spectral theory applies to a self-adjoint operator, or a unitary operator, or more generally to a normal operator. And this is the theory that you find in all your graduate textbooks. But there are operators that are not normal operators, and they have a spectral theory. And this is an example of an operator that has a spectral theory, even though it's not normal. So that's a very interesting factor in operator theory. And it's the source of a lot of work. In fact, I've benefited from it myself in my work. But let's go on. So the operator has eigen functions and eigenvalues. It's clear we're dealing with differentiation. The eigen functions are exponentials. The eigenvalues are complex numbers. But we don't use all complex numbers. We use complex numbers that lie in the upper half plane. The upper half of the complex plane is divided by the real axis. The upper half plane is what's above the real axis. And when we use those complex numbers, the exponential decreases as you move in the positive direction. It's a bounded function. In fact, it decreases very exponentially. And so that means that you have convergent integrals. So the Laplace transformation, let's go into that next. The Laplace transformation, okay, I have a function little f of positive t, and I take the integral. It's at the top of the page with respect to e to the I t z. I call it z now. That'll be defining the eigenvalue. And you get a function that's analytic in the upper half plane. Now what's occurring here is a relationship between Fourier analysis and complex analysis. And this is the beginning of a very happy marriage. My specialty is basically complex analysis, and it has been very helpful for me to start with that point of view to understand Fourier analysis. Now, when you take a Laplace transform, even though it's not a normal operator, there's a spectral theory, because you write z as x plus iy, then as a function of x, you have an ordinary Fourier transform on a line. So there's an isometry for that function of x, but then you integrate with respect to y. This is something new, and you get a new kind of functions. These are functions fz, z equal x plus iy, which are analytic above the real axis in the upper half plane, for which this interval converges, where y is equal to the nu minus 1 power. That's when nu is positive. If you go a little farther, there's also the case where nu equals 0. In the case where nu equals 0, you can't use the other formula. You have to take a least upper bound of integrals on horizontal lines. That's called the Hardy space for the upper half plane. So this is an isometry of a space of square integrable functions onto a space of analytic functions. And the spectral theory says, let's get on with it. The spectral theory says that this is describing the space, I think, all analytic functions. Okay, are we going to, just hold it for a minute. The Radon transformation is unitarily equivalent under the Laplace transformation to multiplication by I over z. So the operator that takes an analytic function of z and multiplies the function by I over z to produce a new analytic function, this is an operator that's defined with domain and range in that space of analytic functions. That operator has very interesting properties. It is accretive. That is because it describes the flow of heat. It is something that is always losing energy when it propagates. The inequalities connected with that Radon transformation, and this is a very important discovery that comes with Fourier, that physical theories need not conserve energy, they can lose energy. And in fact, the flow of heat always loses energy. This is the truth in physics, that there isn't any conservation of energy. It's a lie. We're always losing energy. But of course, people will say, well, the energy is not lost. You can put your hand there and you can feel the energy that's lost. It's just simply going somewhere else again. This is not the theoretical, this is not the theory. The theory says that you're losing energy, and it doesn't say that it goes anywhere. Now, that space of functions analytic in the upper half plane is a Hilbert space with special properties. The taking of function values at points in the upper half plane is continuous linear functional at points in the upper half plane. And so there are elements of the Hilbert space which, used as scalar products, define the value of a function. These elements of the space are called reproducing kernel functions. And for this space, the reproducing kernel function is a function of two variables as a function of z, but there's a parameter that's a conjugate of w there, raised to the 1 plus new power. This function of z belongs to the space, and when used as a scalar product with an element of the space, it gives the value of the function at w. Now, I'm beginning to take too much time, but I would like to come to the end of this section. Let's go a little farther. Okay, I discussed the Radon transformation of order nu. We could go in. I said that in words. I described what's called an accretive transformation. That's the inequality that corresponds to the loss of energy in the flow of heat. And I'm not going to go into that again. It's technical. And let's keep on going. Let's keep on going. I think these are all technical things. And I think, keep on going. Okay. Now I start, this is a repetition of previous material. I think we're in a new section now. And I think we should stop at this point. We're now talking about Fourier analysis, and I think we need a break. In 1884, Nikolai Sonin proved or showed a very important property of the Fourier transformation, or if you like, of the Huncle transformation of order nu for every non-negative integer nu. Now, I have spoken to mathematicians everywhere over 50 years, telling them about this problem. And I have never met, in all that period of time, met any other mathematician that was aware of this contribution of Nikolai Sonin. I think this is a very instructive phenomenon, that it is possible for a person to make a very fundamental discovery in science and in mathematics, and that nobody would know about it or think about it. It would appear in some journal, Mathematische Annalen, 1884, and it would be beautifully printed, and it would be sitting on a shelf in a library. Everybody would say, these are beautiful books, but nobody would open them and know about them. Now, you may laugh at this, but it is a tragedy. It is tragic that this property is not known. And what Sonin showed, he gave examples of functions that vanish in the neighborhood of the origin, if you think of Fourier analysis in the neighborhood of the origin, or if you think of the Huncle transformation, you think of functions that vanish in the neighborhood of the origin on a half-line, in other words, in interval 0a. It is possible to have a function that vanishes in the interval 0a and whose Huncle transform also vanishes in the interval a, 0a, but does not vanish identically. Now this is a very fundamental fact. It means that in a quantum theory, when you have a quantum theory that describes motion of an electron around a solar system, a nucleus, there is in the center there a vacuum as far as the electron is concerned. It's a physical vacuum, but it's also a vacuum in the momentum space. The momentum space is the Fourier transform space of the physical space, and that vacuum occurs in the two spaces together. This physical phenomenon has been neglected, as far as I know, by physicists. Now, the problem, which I take to be the Sonin problem, is to determine all functions that vanish in a neighborhood, an arbitrary neighborhood of the origin, and whose Huncle transform of order nu also vanishes in the neighborhood of the origin. What are all these functions? And I was able to solve that problem in 1964. In other words, a bit more than 50 years ago. It was the first major discovery that I made in my career. And it shaped my career that I discovered this, and I had a difficulty to publication, so it was published in a very obscure journal, so that made it even more difficult for anybody to know about it. Certainly, I wasn't getting any funds for research for doing this. Now, the solution of this problem, and I think I'll describe the solution first so you can see it. Let's get on to the solution of the problem. I do it only in the case nu equals 0, but let's keep on going. I described the calculation, but it's all technical. Let's get on to the answer. Keep going. Keep going, keep going. I want to see the answer, the solution of the problem. It's a little farther. Keep going. By the way, I rewrote all my notes to try to get the errors out of it. I didn't succeed in getting all errors. I never do. But there certainly are very neat, readable notes. You should be, if you want to interested, you should be able to get information from them. Keep going. Okay, now we're going too far. No, I think we need to go a little farther. Let's keep. I want no, farther down. Farther down. Keep going. Keep going. Keep going. Okay. Keep going. Keep going. Keep going. Oh, I went to. We have to go back. We have to go back. I want to find a certain formula to give the answer. We go back. Okay. Okay. I go back a little farther. Okay. Here we are. A bit farther back. Okay. If I have a function of positive t, which is square integrable, and I'm in the case nu equals 0. So this is the ordinary integral square that you use in Fourier analysis. You're familiar with that. It's not the case where nu is positive. If we have a function, ht, I can define two new functions of positive t by these integrals. And the integrals are familiar functions. If you've read the manuscript, they're all themselves examples of integrals with respect to Bessel functions, like you used in the Huncle transformation. But it's a very variant of the Huncle transformation, which I don't want to discuss, but it's a rather curious variant. You may be interested to look at it when you see it. That feature of the transformation is due to Sonin. Sonin didn't, he just gave examples of functions, but the examples work because he used the trick that describes these transformations. So if I have two functions, ht of positive t, I define two new functions by integrals, and go back, keep going. No, the other way. Keep going. Okay, no, keep going. Can I keep going? Okay, I missed something here. I would look for an identity, and I'll say it in words. if I start with a function ht of positive t, which is square integrable with respect to Lebesgue measure on the positive half line, I construct two new functions by formulas. These are functions of positive t that are square integrable, and the sum of the squares of the two new functions is equal to the square of the old function. And also, if we start with two functions f and g of t, which are square integrable, you can construct a function h of t so that we have a one-to-one correspondence between square integrable functions and pairs of square integrable functions. Now, the formulas that are involved here, and I'm not going to discuss them now, are very remarkable because they exhibit the fact that if h, the given function h of t, if it vanishes in a neighborhood of the origin, and if its Huncle transform of order 0 also vanishes in the neighborhood of the origin, then the functions f and g also vanish in a neighborhood of the origin. I'm talking about a neighborhood 0a. It's the same neighborhood in all cases. Conversely, if you start with f and g that vanish in the interval 0a, then the function h and its Huncle transform of order 0 also vanish in the interval 0a. What's involved here is a determination of all functions that vanish in the interval 0a and whose Huncle transform vanishes in the interval 0a. And there's a very remarkable formula that gives that relationship between the functions. So something you see is happening in the plane. Something is happening which people don't realize. You talk to people about the complex plane and its Fourier analysis, and they think it's trivial. But the complex plane has an interesting structure. That structure comes about when you look for functions that vanish in a given interval, and its Fourier transform vanishes in the interval. Then some structure is there, some structure that's something like the Fourier integral, and that people don't know about. Now, I want to describe what that significance of that structure is, and I want to go back to the complex plane, or at least the functions that have a symmetry of order nu, take nu equals 0. The functions that have this symmetry are describing the motion of electrons around a nucleus, and the electrons are constrained. They can only move radially because the circular motion is determined by the constraints that when you multiply by omega, you multiply the function by a given factor. So the only freedom in these functions is in the radial direction. A function, in fact, that's the variable that we use, the function of positive t. T is that radial variable. And when a function when the particle is constrained in this way that it can has only freedom to move in a radial direction, it means that if we have a force-free situation for the particle and you want to pull it in and out and do it isometrically, you don't have much choice. You take the function, here's a function ht, and if you multiply the argument by a positive number x and put a weight of x to the 1/2 power, that defines an isometric transformation of the space into itself. Now, these isometric transformations form a group the multiplicative group of positive numbers. As you know, if you've studied Hilbert space, that the group, it's a continuous group, unitary transformations. It has an infinitesimal generator, which is a differential operator. And so the differential operator, it comes in next. The differential operator is a self-adjoint transformation. It takes a function h of t into, well, basically you have to take the derivative of the function h of t, and you have to multiply by t so that you have this radial action. You have to have a 1/2 h of t because it's a weighting factor in the group. And then you need a factor of I to make a self-adjoint transformation according to the theory of the generation of a semigroup. I could have also put in a positive I there and a positive 1/2 I. I made this negative choice because it works nicely in the formulas that come. So there's a natural structure, a natural differential operator that occurs in this force-free situation that describes the possible motion of the electron as it moves. It can move in and out away from the center. And that differential operator is well related with respect to the Fourier transformation. I don't think it commutes with the Fourier transformation. I think the Fourier transformation takes this operator to minus the same operator. But the idea is that this is essentially an operator that's compatible with the Fourier transformation. So you see in the plane, there is a structure here. There are forces that describe an object that's constrained to this kind of motion, and the nature of these forces is such that it's well related to the Fourier transformation or the Huncle transformation. So in physics, it means that we have a physical space where you have a free particle, and you have a momentum space where there's a sort of a mirror image of that particle. And in the force-free situation, the Fourier transformation commutes or is related to the radial motion. Now, I have a complaint to make about physics, and this is a complaint that you might want to think about. If you read books in physics, they will tell you that the Fourier transformation relates the physical space to the momentum space. And then they will tell you that you can put a force term, a forcing term, so that instead of having a free particle, you would have an extra sort of a potential term, a force term, as in the Dirac system or the Schrödinger equation. And that, again, this would give the relationship between the physical space and the momentum space. Well, there's something about this that I don't understand. Because if you modify or perturb the differential operator, that differential operator is no longer compatible with the Fourier transformation. Now, physicists don't seem to be concerned about this, but I think that every mathematician should think about this. How is it that you have a physical theory that's not logical? You simply change it according to the need of experiment. Something is wrong here, I think. Maybe I don't understand it. Maybe the physicists are clever and they can tell you why this happens. But I don't see the answer, and I think it should be an issue in dealing with the mathematics of quantum mechanics. Okay, now I'm just concerned with the force-free situation. I'm just concerned with the situation where we have that differential operator. Now, when we have the differential operator acting upon h, a first-order differential operator. It's going to cause a differential operator on the f and the g. And I computed that differential operator. You want to go on? And the image in terms of the f and g, it's a differential operator that takes a pair of functions into a pair of functions. And the new differential operator looks very much like the original differential operator. There are perhaps some sign changes, but I think you'll recognize the first part of it is the same. But there's a surprise. There's an extra term that somehow the f and g are mixed in the new operator. So you get a non-trivial operator when you use the Sonine theory. You know, there are physical theories about how electrons move around a nucleus, and I wonder whether perhaps the real meaning of these physical theories is that you are using the Sonine theory to modify a fairly trivial operator to create a more complicated one. I mean, this is a very vague business because I'm talking about the Huncle transformation, and this is a force-free situation. But very likely already, when there are forces present, there's some generalization of the Huncle transformation, and there would be a similar situation that would create what are called Dirac equations for an electron. So I think that the Dirac theory is a consequence of this kind of structure. It's my intuition that it is. It's not anything more than that. We arrive now at a problem in spectral theory. We have a new differential operator that's generated here, and we want to know what is its spectral theory. Well, in my lectures on Monday, I talked about the spectral theory of differential operators, but I didn't look at it from that point of view. I did something backwards. I used the inverse problem. The inverse problem says, instead of starting with the physical space and the differential operator and get the spectral theory, I started with the spectral theory and used the inverse problem to get the physical problem. Now, people in physics and applied mathematics, they believe that it's possible to go backwards, but they just assume that it is so, and it's not. There's a theorem. In fact, it's my theorem that there is a unique inverse problem. I don't know how to solve it, but it has a unique solution, and so the reverse process is compatible. But now I've caused a lot of difficulty for you in this lecture because I approached this differential equation in the first lecture with a spectral theory, and in the section lecture I started with a differential operator, and now I have to relate the two. And this is difficult. It's difficult because I'd have to write a lot of formulas down, I'd have to check them, and then you would certainly get bored seeing a lot of formulas and computations there. So you'll just have to take my word for it that these two things come together, and that the spectral theory that you get here is an interesting special theory. In fact, the spectral theory is a theory of what I call Kummer spaces. Kummer was a mathematician in the 19th century, I think probably mainly in the first half of the 19th century, going to the middle. And he's known because he showed that in an algebraic number field, you have a factorization theory. You have to use ideals. He introduced the concept of an ideal in order to describe factorization. So even in an algebraic number field, you have a factorization theory that something like that of the integers, but it doesn't have a uniqueness of factorization. there's not, in general, not a Euclidean algorithm. And he showed how to deal with that situation when you don't have a uniqueness of factorization. This is a very good, important contribution to mathematics, and any algebraist respects that and knows about that. If you're an analyst like I am, you're a bit more distantly related to these algebraic number fields, but I think we all know there is such a theory and that it's an important one. Now, what people in number theory and algebra don't realize is that Kummer also made an important contribution to the hypergeometric function theory. The hypergeometric function theory, according to, it's really due to Euler, but Gauss gave the most popular exposition of it, so that many people think that it's the Gauss hypergeometric function theory. That's not true, but certainly Gauss gave a very nice description of it, without giving any credit to Euler, by the way. That theory is one that you know, where you have power series for functions. But in the confluent hypergeometric function theory, again, in some cases you have power series, but there are solutions of the differential equation that are not represented by power series. So Kummer worked out these other cases, they're integrals, and at this point many people would say, well, I'll believe it, I won't work it out, but it's a very important theory. Now that Kummer spectral theory is what appears in the solution of this problem. So you get one of the few examples of computable spectral theories that appears here. That gives the significance of it. Now, I think I've exhausted all the technical material I have here. We've come to the end of the lecture, and I'm not going to give any more details of that. But again, I would like to say what the significance is of the complex plane. The complex plane is a model for a locally compact abelian group. It's a special kind of locally compact abelian group. How much time do I have? It's okay?
Yes, you have 10 minutes.
It's a special kind of locally compact abelian group because there's a conjugation for the multiplicative structure. So it's not the most general locally compact abelian group, but it is a very general one. And the things that happen in the complex plane have a generalization to all these groups. So we're not dealing with a very special theory. We're dealing with a very general theory, or one that's capable of being very general. I'm still doing my homework to work this out. Now, what happens in a general locally compact abelian group? Well, it's going to look like the plane. There's going to be a compact group that describes symmetries of the object. And then there's going to be a radial group. And that radial group is the positive half-line. So every locally compact abelian group that has the conjugation resembles the complex plane. This is a very important discovery because locally compact abelian groups are used in number theory to describe zeta functions. I think they should be used in quantum mechanics. The groups of quantum mechanics that are now used are very restricted. They're essentially Euclidean type groups, and I think that you should also have the p-adic groups in there. But in any general situation, you have essentially what's here. You have a compact group. Now, a compact group, it's not commutative, will have finite dimensional representations. That means that it may be painful to write out the work, but you know, there are lots of people that like to do representations of groups, and you can probably look up the answer in a book if you don't want to do it yourself. In some cases, you'd have to generalize a little bit. So these locally compact, these compact groups, well, they're not trivial, they're not elementary, but they're a known object. And all the analysis that you have then is occurring in the radial direction. And we get all the analysis in the radial direction when we work with the complex plane. So you see, this is containing a lot of information for the applications of Fourier analysis. The applications both to quantum mechanics and to number theory, all that information is present here in the complex plane. I have a feeling now that I'm losing control of the things that I want to say. I'm moving into areas where I would become technical and incoherent. Perhaps I've already reached that stage where I've become incoherent, and I'm afraid to move on. So I would like to stop at this point where I still know what I'm talking about.
Thank you very much. Are there any questions or comments? Yes, please.
I'm sorry, I wasn't able to attend all your talks, so possibly you already said about
Let me try to...
something about this. So did you try to study zeta functions or general arithmetic schemes using your methods?
So there would be general, the simplest one would be general zeta functions for modular forms. They would be contained in this theory. That's a fairly general theory already.
I think it's a little somewhat different direction. So I don't know much about modular things, but I think it's not a problem. As far as I know, there's not a problem to analytic deviation is known for modular things.
Yeah, well,
you have
a good point. I'd like to take up an issue that's come up here. You know, if you talk to somebody in number theory, they will tell you that there is a very good number theory which is based upon what's called modular forms. Well, let me tell you, if you start with number theory from modular forms, you're losing a lot of structure because these modular forms are really the Laplace transforms of something that's happening on a locally compact abelian group. And if you stay at the level of the modular forms or the Laplace transforms, you're missing all the information about what's happening in the basic space. For example, we need this information from the Sonine theory. We want to know functions that vanish in the neighborhood of the origin and whose transform vanishes in the neighborhood of the origin. Now, if you look at modular forms, you don't even see that space. You can't even formulate the problem. And for that reason, it will be very difficult by these methods to say, suppose you want to prove the Riemann hypothesis. You don't have any information for doing it. You're not going to succeed. But if you go back to the locally compact abelian group and you deal with the Sonine problem, what you have is a structure. You have a differential operator. Something is happening. And the spectral theory of that differential operator is going to give you these zeta functions. So there's another way to get the gamma function and the zeta function that's going back to very fundamental Fourier analysis rather than the sophisticated analytic function theory that comes from the Laplace transform. And also, if you start with Fourier analysis on a group, there is a Radon transformation. There is the flow of heat taking place on that group. And the flow of heat loses energy. There's a positive sign. Something is happening that is constraining the function theory. And I claim, or I believe, that what is happening is that positivity is denying zeros. Zeros cannot appear in certain places for gamma functions and zeta functions. And the absence of zeros is a distance. You have the real axis, complex plane, and the upper half plane and analyticity. And you can go down below the real axis to a distance exactly 1/2. And there will be analyticity and no zeros. Now you don't have any hope of proving that if you don't have the flow of heat, if you don't have the Radon transformation. You're missing the structure that gives the motivation or the possibility of proving the Riemann hypothesis. So does that answer your question now about why you shouldn't be dealing with modular forms? The modular forms are at a higher level of the Fourier analysis, and you're missing information if you stay at that level. You have to come down to a more basic level where you can formulate the Sonine problem.
Actually, my impression on this subject is that there are some functions that come from modular forms and other functions that come from arithmetic schemes, say, or from elliptic curves or over number fields, but I'm not quite sure about the relation between these two.
Okay, now these theories are rather complicated historically, and I'm familiar only with Fourier analysis and its consequences, and I'm really not knowledgeable about very algebraic or other techniques of analysis that exist in the literature. So it's not, I can't answer. I mean, elliptic modular functions, something I don't understand.
Modular functions, you just take some product, or Euler product, and say this is a zeta function.
You're outside of my knowledge.
Okay.